Hi, this is Jordan Stevens and Danica Dvorak. Unfortunately, we could not meet this week to do this video together. She's going to be doing homework 7, I'm going to be doing homework 8. So moving into this, we're going to be doing the section 2, problem 2. This is basically modifying the generator, the multiplicative generator that is stated in the book. The problem is basically here. We're going to use procedure R1, and we're just going to kind of mess with it a little bit, change out the A value and the M value, see the results from it. And from this, we're trying to basically observe the period and verify it agrees with the theory. The theory that they're talking about is this one below, basically saying that if there is a multiplicative prime modulus, this is a multiplicative prime modulus, that you want for the max period, the A to be the primitive root of M. So for the larger the period, the better in generators, and we want the A to be very, very long. I mean, we want the A to be a primitive root of M, so that it's very, very long. So we want this 7 to be a primitive root of 61, or the 49 to be a primitive root of 61. So that's the theory we call upon. And then finally, the R1 procedure that it's referencing in the problem is just this. This is it written in the Mabel code. Basically, this is just kind of what it goes through. It's a typical procedure. So moving on, we're going to talk about primitive roots. I just plugged this into Wolfram Alpha. That's the quickest way to find primitive roots really fast. So I found out that 7 is a primitive root of 61, but 49 is not a primitive root of 61, as by here. A primitive root just basically means that it is 7 to the first power mod 7 is equal to 7 to the 61st power mod 7. So basically that to the power of the 61 is equal to that to the power of 1 modulus that number. So here's that. And then let's move on to our MATLAB code. Here's the one for the 7, here's the one for the 49. It's just generating from 1 to 100. I was assuming that the period is less than 61, as shown by theory. And to find the actual period, we use the seqperiod function in MATLAB to find the actual period of the sequence. So moving on, here's our results. As we can see, it starts to repeat after about 60, as you can see right here. So yeah, it's exactly 60. And since we know that the max possible sequence of random numbers is 61, 60 is actually really good. And then moving on to the second one, for 49, we see that the period is smaller, which validates the theory that if it's a primitive root, it will most likely produce a larger sequence of random numbers, and this can be shown that it's about 30 in the graph. So with that, that concludes homework number 8.